All right, good morning. Welcome to day 2 of NeuroHackademy. It's great to see all of you here on my screen and in front of me. And this morning we're going to start, so just for framing, there's going to be a series of Python things. And in the other room, Noah's starting with sort of intro to Python. And in this room, folks who are entering, maybe drag in some tables and chairs from over there. Here we're going to do a series of little various things related to Python. So today it's going to be Python. We're going to focus in particular on Pandas, which is an excellent library that some of you may have used. And if you're like me, then maybe you learned Pandas by using Pandas. And I think it's sometimes useful actually to step back and think about what Pandas does and why it does it, and like how that relates to other things. So I hope to give you some of that today, while also, of course, teaching you about Pandas. To do this, you could follow along. Let me share my screen here now that I've rambled for a little minute here. So what I'm going to do is I'm going to go to the neurohacademy.2c.cloud hub, and something like this should happen on your screen. Something like this should happen on your screen as you log into the hub through your web browser, and eventually you should end up in something like this, although it should look more like that. Well, maybe you won't have. Well, you should have in your home directory in the hub, you should have 2 folders, one called NH 2022 Curriculum, which is we have the hub cleverly set up to pull from a GitHub repository that contains all the curriculum. And so we can keep updating the curriculum during the week up to the last minute. And then when you click on that, that will be the most updated version of the curriculum. And then hey, Mackenzie, one thing I realized is we don't have any power cables in here. Would you mind grabbing a few? Oh, for everyone, yeah. So thanks. So this curriculum folder should contain a bunch of folders in it, and each folder pertains to a particular tutorial session. And we're here in Rokem Pandas. It's instructor last name dash topic. And in here, there really is just one notebook that we'll go through during the next hour or so. And that will be about munching data with pandas. Who here, I won't ask that. Instead, I'll just assume you've never used Jupyter before and just give you a short introduction on Jupyter, because this is the first time that we're using it. And this interface is called Jupyter Lab, which even if you've used Jupyter, you might not have seen this. It looks a little bit more like an integrated development environment because it has some interface to folders and files here on the left. And then this plus button here is called the launcher. And that'll take you to this kind of screen, which allows you to launch various things. You can launch a terminal by clicking on the terminal. And that's a standard Unix shell that we'll use later today in our GitHub tutorials. If you go to the launcher and you instead click on this Python 3, that brings up a Jupyter notebook. And in this Jupyter notebook, you can type code, import numpy as np, and to execute the code, you hit shift and then enter. Oh, this is small? Yeah, can we get it slightly bigger? Yep. Oh yeah, I should get rid of that. Let's always an issue. Let's put it down here and hope that it doesn't get too much in the way. I'll minimize you folks on screen, and I'll just remind you all that we have a channel for this. It's under Rokem Pandas here, and you can join that. And if you have questions, type them in here. And I won't necessarily see that because I'll be in Jupyter, but folks here in the room will like butt in and say, hey, there's a question on Slack you should address right now. So I'll appreciate that. Okay, and then once you have that, you can write some code. Here I'm creating an array. And if you don't assign the array into anything, then Jupyter will kind of spit it back at you. It generally spits back at you the last thing in the cell, but you can assign it into a variable, and then maybe plot it, and then plots appear inside this document. So that's Jupyter on one leg, and we'll do a lot more Jupyter in this course. You'll see all kinds of use cases. Okay, so pandas. Why pandas? There's a term, data munging. Has anyone heard the term data munging before? Data munging. I looked up the etymology of this. Munging is like something that you do with grain in order to separate wheat from chaff, so to speak. And in data science, we talk about data munging as the process where we go from some kind of raw data to data that's useful to us, data that we can analyze, we can visualize, we can interpret. And Pandas is a great library for data munging. But actually, in neuroscience, data munging is a whole set of things, right? Because you start with some images and you have to do some image processing and do some transformations on that, and maybe you derive some quantities from that, and then you get, if you're lucky, you get to a big table of numbers that you can do statistics with. And Pandas is primarily interested in that second part. Your data is already in a table, and you're doing some things with that table. There's some data munging to do there as well, because maybe you want to do some selection of observations, or maybe you want to group them in certain ways. And that really is what Pandas is all about. We'll come back to this idea, but Pandas really is one way to think about it. If someone here is kind of like in computer science, or is an in-memory database, really. So if you've worked with database systems, Pandas, a lot of what Pandas does will be familiar. But also, if you've never worked with databases, and I've rarely worked with databases, if you know Pandas, you already know a lot about what databases do, which can be quite useful if you ever have to work with a database. Okay, so having said all that, let's start with an example here of the kind of data that we'll work with in Pandas. This thing here is standard Python dictionary. And I've stored data in a dictionary because I have data that's complicated. It's a group of fruit and their properties. And each fruit has a unique ID associated with it, has a price associated with weight and deliciousness. And each list here is coextensive. So this apple here is the one that has the unique ID A101, and it has the price 0.1. And this is in some sense a really good way to organize data, because we have a set of lists that all correspond to each other. If we know where each, if we want to know what price the apple with the UID A101 has, we go to the first item here. But on the other hand, this is really, really clunky. Like you can imagine, if you've worked with Python dictionaries, think about trying to write the code to display the average price of oranges given this data structure. It's really clunky. And so what Pandas provides is a data structure that is much less clunky than that. I should say, if you work with NumPy, you look at this and you say, maybe I should put this in a NumPy array, but a NumPy array will not take this data. Anyone here or there have a kind of a sense of why NumPy will refuse to look at this data?
Yes, data set.
Sorry, yeah, go ahead.
We have mixed types of data types here. That's why.
Yeah, exactly right. It's mixed types, right? There's some strings over here and some numbers over here. So NumPy doesn't know what to do with this. NumPy is really great and fast for data of fixed type. So if you have images that are all floating point numbers, or then the NumPy is your thing. But here, this is mixed type. So NumPy won't work with that. Okay, so on to Pandas, which will work with mixed types. Pandas, sure, it's an animal, but it also stands for panel data, which tabular data of this kind sometimes is called panel data also in some fields. Pandas is extremely popular in the data science world. It's become really foundational since since its creation, and now you'll see it being used in many as a dependency of many Python software libraries, including many for neuroimaging. You'll see that later this week even. So we'll import pandas as PD. That's a common convention, sort of like I imported NumPy as NP. We import pandas as PD. It's not required, but really is a strong convention. It'll confuse anyone reading your data if you import pandas as anything else but PD. The main object that we use in pandas is called a data frame. And the data frame can take its data from many different sources. In this case, I am going to take it from this collection of fruit from a dictionary that contains the data. That's one way to initialize a data frame, and we'll see a couple more. In Jupyter, once we do that, we get a really nice representation of the tabular data as a table in the notebook. So we can see the tabular structure of this thing. And once we have that, we can start doing what we call querying the data. Querying, it's a fancy name for indexing into the data, or selecting parts of the data. We can query by column. So we have here different columns, right? The original keys in the dictionary become column titles here, and the values become the values in each row. So for example, here, this is the key UID. It became the column title here, UID. And these values here got assigned into these values. And you can see there's rows and columns. And that every pandas table has rows and columns. So we can select by columns. So this is an indexing operation. In Python, indexing is done with the square brackets. And here we're indexing with a string. And that string is a name of column here, or a key in the original. We can think of it as also a key in the original dictionary. And that'll give us back this series of kinds of fruit, apple, orange, and banana. We can also do something that's fairly useful, which is to say, let's think of this unique ID, because it's a unique ID. Let's think of this unique ID as an indexing variable. This is the variable that we will use as the index for this table, and we can create a new, or copy over, assign into a new table called the same thing. The fruit table having set the index to this UID. So let's look at the table now. You'll see that it's slightly different. In the original table, what Pandas does per default, it says, you didn't tell me what the index is. You didn't give me anything to index on. I'm going to create a serial index, 0, 1, 2, 3. That's the leftmost column. And that will be my designator for the rows. And you can use that as your index, because I have to have an index. Here instead, the first column on the left is the UID column, and it's bolded in this display, and it is now the index column. And so we can use the index to query on the rows of this. For example, by saying, and now we're using a different kind of indexer, right? We used the indexer square brackets before. Now we're using the LOC, or lock indexer. That's a really weird thing. It looks a little bit like a method of the object, like a function that is attached to the object, but we don't call it with round brackets like we call usually functions in Python. Instead, we call it with the square brackets as an indexing operation. And this really is what this is an object, or an attribute of the object that lets us index into it. And so what we get when we do that, indexing in with one of the index values there, is one row from the column, and all the values. And you can see it's got the same tabular kind of format with the column names now on the rows of this new object. We can combine these to query the table both on the rows and the columns. So here I'm calling lock with an index on the first dimension. It's an index on the second dimension. If you've used NumPy arrays, this should look familiar to you in some weird sense, because this is an indexing operation on 2 dimensions. And we do that when we have more than one dimension of a NumPy array. We index on the different dimensions by separating those dimensions by a comma here. So we're indexing on the first dimension here. That's the row dimension, and then the second dimension here, which is the column dimension, to pull out just one value, this value of the price. And this is, once we did that, we got a single number out of here, 0.1. This thing really is just a floating point number, not just, this is a floating point number in Python, 0.1. And then we can do something that is also a standard Python thing, which is called slicing, which is to say that we index from one position to another position on one dimension, and from one position to another position on the other dimension, to get sort of a subtable in this case of the original table. Yeah, so this is called slicing, and in this case we're slicing on both dimensions. You don't necessarily have to do that. We could say I want everything between A101 and O102, just the price, or I can go back and get price through weight, right? So I'm getting this weird subtable. Do you notice anything weird about the slicing operation? What's weird about the slicing operation? Yeah, so one thing that's weird is it selects a certain range here, as pointed out. So things that are back to back. Yes, and it can select. So I selected in this case, I guess O101 through O102, but I could also select, through BO101, say. And that will be smaller now, right? So, but it can only select in between those. I can't, using this particular operation, I can't get a selection of rows. And I agree that that's a weird thing to do. So this looks like a weird thing, and we'll rarely ever do this, but it's good to think about. I think it's good to sort of understand that Pandas under the hood is a Python data structure. We'll see how we actually operate on Pandas to get useful things. Anything else that's weird about this slicing operation? Yeah. Sorry.
The slicing in this case is inclusive, so like the last thing included.
Yeah, so that's exactly right. Slicing in Python is usually exclusive of the last item, right? When we slice between item 0 and item 10, we get everything except for item 10, up to and except, but not so here. So this is weird, but so it goes. That's how Pandas works, because probably when you do this, you intend to, you're not intending to get everything up to this, you intend to get that. So that's how it's designed. But that's just something to note. There is another kind of indexer called iloc, which will index into the rows and or the columns by their serial position. So this is the first row, and this here is the second row, and here is rows 0 through 3. And in this case, it is exclusive, as you might expect. Yes, I'm trying to do this so I can hear you.
You said that we can only slice like sequential numbers, but if you put a list that you can select anything that you want.
Yeah, 100% correct. Yeah, we can do 0, 1, 3 like that, right? Skipping 2 along the way. Put that inside of the list, and you get those items. Sorry, I'm going to turn this back on. So, but yeah, I'll turn this off every time I need to talk to you, because I'm in like this bubble of white noise in here. It's tricky, and my hearing is not that great anyway. So, okay, so this is a lot more natural to do. Any thoughts about why this is more a natural thing to do with this kind of data? Yeah.
And that's based on an ID, not based on order.
Yeah, the order in tabular data, the order is not necessarily, the order of the rows may not always be a meaningful thing. Sometimes it is, but often you get tabular data, and after you start manipulating it for a little bit, the order stops losing its importance as much. So it's kind of a weird thing to do, to use the rows. So I'd warn against using iloc unless you have a really good reason to select by the row order. Okay, let me pause here for a second and see what questions do people have so far. about all this. And let me turn to look here and see if there are any questions here as well. I see no questions. Good. Okay. So I'll carry on here. So now we've learned how to do some very basic operations with pandas, data frames. Let's think about computing with data frame objects. Data frame objects have methods, functions attached to the object that can do computations for us. For example, much like the NumPy array object, there's a mean function, and it really only makes sense if you say numeric only. For this case, I can show you what it looks like if I don't say numeric only. It actually warns me that in the future, if I don't say numeric only, it'll think that I don't know what I'm doing, and so here numeric only. But really, an average only makes sense for numeric values, and so it really just gives me back the averages of the numerically valued columns here: price, weight, deliciousness. And there are other methods of this sort. We'll see a few more methods of this kind a little bit later. Maybe a little bit more interestingly, we'll come back to computing with data frames in just a second. More interestingly, we can start doing computing with kind of subsets of the data frame, with different parts of the data frame. But before we go to that, let me go back to this selection that I did before. So before I said, hey, you can select a column by indexing with the square bracket. The natural indexing operation in pandas is to index by column, and this gives you back. I mentioned this word, but it's important to pause on that. That gives you a different kind of object. This is no longer a data frame. It is now a pandas series instead, and a series is one-dimensional. And so here is the series. Let me put it in here. Fruit kinds. By the way, I use a lot of Jupyter shortcuts, and I just did use a shortcut. This shortcut that I like is Control M and B, which puts another cell below, or Control M and A, which puts another cell above the cell that you're in, and that's pretty useful when you're teaching and you want to put in a quick cell where you are. But I did that really quickly, so I thought I'd pause and mention that. Okay, so this kind of object, the series object, lends itself to Boolean operations. We'll see in a second why that's really useful, but I'll just point it out here. We can say fruit kinds equal orange, compare it to a string, and then assign that into a new variable called isOrange. And isOrange is another series object. Again, it's a one-dimensional object, this case with Boolean type. And it's got falses wherever the fruit kind is not equal to orange, and trues wherever it is equal to orange. In this case, there are two oranges in this collection of fruit, the second and the third rows, and so that's where this is assigned to true. Now, in NumPy, we often use Boolean arrays in order to index into an array and select certain values. Let's say I have a big array with numbers, and I'd like only the values that are larger than some value. I might do something like, I'll write it out, array in array larger than 10. And this gives you back all the values in the array that are larger than 10. Here as well, and that's because under the hood, pandas data frames are NumPy arrays. They're derived from the NumPy array. We also use Boolean indexing. So we can say, give me back fruit table where is orange. And that gives me back the rows where the series is true. Notice that the index has come along for the ride, and that's important under the hood, important to be able to do this operation. But for our purposes, it's not that important. It's just important that we can do this kind of thing, series of things. We can find where, we can find the column called fruit kinds, and then find where the fruit kinds are orange by a comparison, and then use that to index, or in one fell swoop here, create a new table. So this contains all of those, right? Fruit table kind selects for the kind column, equal orange does the comparison, and then that whole indexing operation in here indexes into the original table to give us the orange table, and now we can proceed to calculate the average price of oranges in this thing by using the mean operation here. In this case, I've actually selected only the price column first and then calculated, but I could also do the opposite, I believe, price like this, which will throw that ominous error because this table has both numeric and non-numeric values, as you remember from before. So here I need to say numeric only equals true, and then I get the same value regardless of the order, the exact order that I do this. So here it is in one call, right? So we can do this. So here we're starting to build a language for querying things and computing and kind of like selecting useful things. Let me pause here. What questions do you have about this whole thing? Yeah.
So, for example, you can imagine that you have like a vegetable table that has the same number of rows.
Yep.
And Pandas would allow you to index on like vegetable table kind equal broccoli, even though it's a different table if it's the same number of rows. Like, is there a way?
Yeah. Although that's I don't know. Like here I've written out the thing you're objecting to. This is not nice because here you had to write food table again. That's kind of clunky. Is there some way to say like, hey, look into this table? There might be, but I don't know. Looking around, maybe somebody else does. And we'll look at what happens when you have more than one table in just a second here, or a few seconds actually. Okay, sorry, I turned that on before asking what other questions do people have at this point. All right, I'll keep going. You can also compute with the series themselves. So you saw how you can select series. Those are like the columns here. You can also do computations with the series. For example, you can take the column designated as weight here and divide it each by 1,000 to get, I failed to say before, these weights are of course in grams because we're scientists and SI units and whatnot. So here I'm dividing by 1,000 to get the weight in kilo. And that gives me another series. It takes every item in this series fruit table weight and divides it separately, item by item, by this scalar, 1,000, to give me the weight in kilo here. Interestingly, as I've written here for some reason, but very usefully, we can start changing the table itself by assigning back a series. If the series has the same index and the same size as, or same number of rows as the original table, it can very straightforwardly become a new column. Here I'm assigning into a column that doesn't exist yet, saying here, create a weight in kilo column and assign these numbers into it. And lo, the table changes, it adds a column. This is quite different from, say, NumPy arrays, where this operation would cause all kinds of mayhem, and is really, really useful. So you start doing computations and storing them back into your data structure. This is very, very databasey. You can also do computations between two series. This proceeds like computations in NumPy in the sense that it does the computation item by item. And really, when you think about it, this is what you want. You want, for example, you want to compute the price per kilo here. You want to take all the prices and divide each price by the weight in kilo to get this table here that has now the price per kilo. So here in this case, we've selected one column, divided it by another column, and assigned that into a new column. What Pandas does is it gives us a new table, or it changes the table in memory into a table that now has row by row price per kilo computed. Let's see. Knowing all this, let's spend a minute here on this exercise. How would you compute a deliciousness per dollar index for these fruit? Just think about that for a few seconds here, and then maybe try it in your notebook if you're working along with me.
Well, what is shortcut for?
Oh, to create a new cell, you can do one of few things. Edit. No, I'm totally wrong here. Plus creates a new cell, but there's also the shortcut that I showed you before, which is Control M B, like that, which adds a cell below, and Control MA adds a cell above if that's what you want to do. Sometimes you want to do that. Okay, any ideas about how I would compute a deliciousness per dollar index for these fruit? Someone come up with a good computation you'd like to share? I'm guessing, is there anyone on Zoom who has an idea? Do you want to share your screen and show us? Oh wait, oh yeah, if you share your screen there, we can all see you. Then do you want to do that? Let's try it. What's the worst that can happen? Or was there a question from Zoom? Sorry, okay. Anyone want to? Yes. We're going to call that delicious per dollar. We need an acronym for that, of course, to make the paper harder to read. What was the? Oh, and I hit the tab complete. Pandas is really clever. It knows how to tab complete from your. Oh, sorry. What was the next operation? Table. And then it even tab completes to tell you there are a few things that start with PR. Let's take price. And there you go. Apples are, of course, superior to anything else. The national fruit of Washington, the state of Washington. I think this even works if you do price per kilo, right? Of course, apples would be superior in any comparison. So you could also do this. I didn't quite specify, should it be like weighted by the weight or not? I think you could reasonably also argue for this one. Okay, but anyway, those are computations with series. Okay. Let me pause here again just to see what questions people have at this point before we move on to the next kind of challenge here. Okay, yeah, usually, actually, when we work with data, any reasonable data set, we'll probably have the data already in some file and we'll want to read it. One of the maybe little admired magical powers of Pandas is how many different data formats and across how many different kind of modalities Pandas can read data. It can read data from open data formats like CSV and TSV and Parquet and a very large number of those, but also proprietary data formats like Stata and Excel. And it can read data that's stored on my hard drive right here. It can read data over the network. It can read data. If I give it data that's stored in Amazon S3, and I give it an S3 address to a CSV file stored in Amazon S3 into this function called pd.readcsv, they'll just read that if I have access, if I have the credentials to access that data. So the ability to read data is really quite remarkable. But also, when you think about it, it's kind of for most of us, that will just be this simple function here, read CSV. In this case, we're going to read a TSV file. So it's separated by tabs. So I have to tell the read CSV function that I have stuff stored in a tab separated value file, not a comma separated value file. But it can do that, and it can deal with headers, and it can deal with, it does some, it has some reasonable assumptions built into it about how to read the data. In this case, the data is from this paper by Bethlehem et al. Looking at a data set called Abide2. Abide2 is a large consortium of groups who've all together banded to collect and aggregate data measured from individuals diagnosed with autism and control subjects. And here we've taken the data that these authors have put together into a big table, analyzed the data and put together into a big table that contains a few features of the subjects, as well as a lot of features of their brain derived from FreeSurfer. So we'll see what that looks like in just a second. Here I am. The data should be in this shared folder, and you should all have access to it on the hub. Shared contains a bunch of, I should say, a bunch of data sets that we put in there to share among everyone. We have a useful way to store this only once and make it accessible to all of you. Later on in the NeuroHackademy, there's some particular data set that you want to share among people. Just let me know and I'll put it there. I have the ability to put it there. This folder to you is read-only, so that there's some control over this. But if there is data you want to put in there, we can put a lot of data in there for your hack purposes. Okay, so I read that and then I look at the shape. So there's 1,004 rows here and 1,446 columns, quite a bit larger than the 4 fruit that I had before. When I display this in the notebook, you'll see that it displays a lot of these rows, but definitely not everything. We got these dots here to indicate that there's a lot of rows in between. And it'll display a lot of the columns, but also not all of the columns because there's lots of columns. And there's some dot here in the middle just to indicate that this is much larger than what is displayed on the screen. But you can already start seeing some of this, and it's pretty useful actually to look at your data just to see, what kind of data types do I have in here, what kind of variables. For example, here you'll notice that there's a whole bunch of things that start with FS. Those are columns that are FreeSurfer derived, first area, left V1 ROI, left MST, and so on. And then there's actually other things, cortical thickness. There are a few different, I think there are 4 different properties derived from FS for FreeSurfer for 360 ROIs, I believe, from the multimodal parcellation, the HCP multimodal parcellation. So great data set. We'll look at it later in the week as well, because it's so useful for many things. When the data is this big, you sometimes want a quick summary of everything. Describe is a method that will describe the data to you. Again, it'll, because there's so many columns, it won't actually describe all the columns, but for every column that you can see, it'll show you the count, how many variables are are valid values, are not a number. Sometimes you'll have like not a number or an A, not available, or some kind of null values in there. So these are the non-null values, and this is full for all these columns. The mean, standard deviation, and quantiles of the distribution, including mean and max, and then the quantiles here. So it's kind of neat to look at that. You might look at this, for example, if the minimal age here was a negative number, that would be a useful thing to know. If the maximal was, like Russ's example yesterday, something in the tens of the thousands, that would also be useful to know. So this kind of gives you a glance of the data. So I should say there's a few columns here in the beginning, a very important subject identifier. In this case, it's a numerical identifier. So these numbers don't actually make much sense. This kind of like a unique identifier. There's site. Site didn't come in here because it's not. So there are several different sites here. We can look later and see how many sites. There's a subject identifier, age residual. This age residual will come in handy when we talk about this data in the machine learning session later this week, and is the subject's age relative to their site. Because there are different sites here and there might be differences between the sites. Hint, hint. Sex coded as 1 and 2. I actually don't know which is which here. Maybe there's a lesson to be learned here. Maybe you want to name your column is female instead of sex and coded as 0s and 1s. There's group. Group I actually do know. I think I wrote it down here. Group is 1 indicates autism diagnosis and 2 indicates control subject. So we know that at least. I could probably look this up somewhere in their paper or where they put the data on GitHub, but I haven't. Okay, so this is realistic data in the sense that it really is real data from a real neuroimaging data set. And so now the question is, what do we do with pandas in order to use this data? We can do things like we did before, right? Start calculating, start selecting rows. I don't know, I want only the subjects that are above some age. or only one of the groups, and I want to calculate means of some of these columns. And we've seen the building blocks for all that before. But I'd like to sort of move a little bit further here to introduce a really important paradigm for analysis to you called split, apply, combine. Split, apply, combine, it again comes from sort of the database world, is the idea that when we're faced with a data set like this, many times what we'd like to do is we'd like to split the data on some attribute, for example, on the group variable, and we'd like to do some computation. We'd like to apply some computation to each one of these groups, or the subsets that we've grouped by. And then we'd like to combine that in the end into one data set that summarizes this original data set. So that's called split, apply, combine. Just out of curiosity in this room and on Zoom as well, give me a thumbs up or hand raised if you've heard of split, apply, combine before. If this is like something that, okay, so several of you have, and that's good. And I'm trying to calibrate to see like, well, folks, this is the kind of thing that when I was first exposed to pandas, I didn't learn it that way. I learned like, here's some code that uses pandas, go. And then only later did I go and read and realize there's these things. So I'm curious to hear that. So the way that split, apply, combine, one of the ways that split, apply, combine is implemented in pandas is via a method called group by in the data frame. So I should go back and mention, I read in here, and I kind of did that quickly. I read using read CSV, I read from the file and assigned that into something I called features. And then now I have a data frame called features, and that data frame has a method group by, and I can give it a string that tells me which column I would like to group on. And the resulting object is strange. It doesn't really have a nice display in the notebook. It's this generic data frame group by object. And the reason it doesn't have a display is that we really want to do something more here. This is just the first step in this split, apply, combine. We really usually want to do something more here, which is to apply something to this group by. So we rarely really ever look at this by itself. Rather, we do something more. For example, we can apply a variety of data frame methods to this object. For example, here I have this group by object. I can apply the mean to that, and I get a new data frame. So the result of that is a data frame, and this is a data frame that has only 2 rows in it, one for each of the original unique values in this group column. So I get a very, very succinct data frame, very small. It's got an index column. That index column is named after the column that I used for grouping. It's got just 2 values here, and then it's got a mean for every one of the numeric columns in the original data set. So I can go and I can directly compare, look at this and compare, I don't know, the ages or the area of the MST, left MST ROI in the 2 groups. I can look at that and directly do the comparison. So let me pause here and see what questions you have at this point about this. The group by operation. So this was the full split, apply, combine. I split, I applied, and then it combined into this new data set. And I could do more combinations later, of course, if I've done this with other group or other subsets of the data, I can kind of combine those in various ways. We'll look at that in a little bit. Yes. That is a great question in the sense that that's exactly the next thing we're going to do here. Before I do that, though, what other questions do people have about this group by? Yeah.
The group back here is the parentheses, and sometimes like previously I use the bracket, and this one.
Wait, hang on, like this. I don't do. No, but we'll see the square bracket coming in very soon. You probably mean something like this. And that would work just as well. And the reason for that is that sometimes you want to group on more than one column, and then you really need that list. So let's move to that. Here, instead, so the question here was, what if I want to group on more than one thing? I have group and I have sex. Maybe I want to know how things kind of like split into these four, the 2x2 combination of group and sex. And here, and this is similar to the indexing operation in the columns originally. If I wanted to select more than one column from the data frame, I'll demonstrate this with the fruit, actually, why not? Fruit table. Let's say that I want to index on kind and price. I need to give the indexing operation a list of columns here to get both of those columns. And this is it's a natural thing to want to do. Sometimes I want a subtable that only has certain parts of the table. So I could do that with the list. And in a similar way, I pass here a list of columns to this group by operation. And I do the same thing that I did before, but now I do this with these two kinds of things, and I get this table here. This table is a little bit more complicated than before because it has 4 rows. We have 2 index columns here. So this becomes a little bit more complicated of a table because it's got 2 index columns. We call this a multi-index data frame. It's got a multi-index because it's got 2 index columns. And so the first 2 rows here belong to this group 1 and has sex 1 and 2. These 2 rows down here belong to group 2 and have, again, sex 1 and 2. And now we can get like the cross tabulation, essentially. For every one of these, the cross tabulation of group and sex on each one of these properties, we can start doing statistical comparisons of, this lends itself to 2x2 ANOVA. Or this is the average for the 2x2 ANOVA. And then we can start selecting here as well. Remember that when we use lock, we can use the first index when we use lock that you saw at the very beginning is the index on the rows, and it uses the index column. In this case, the index column contains values that are numerical. So if I index with 1 here, I'll get the subtable that is the 2 first rows of this 4-row table, the one that pertains to group 1. And similarly, if I put 2 here, I get the second group. This is not to be confused with ilock1, which would confusingly enough give me this different thing here, right? This is the very first row in the table, or sorry, this is the very second row in the table. So this one letter difference here is really important. It will really change the meaning of what you're doing. But we can start selecting, and we can start doing fancy stuff like group comparisons. So here we can look at the difference between lock 1, in this case, because it's a multi-index, the second index is the second value in this indexing operation is into the second index column. So when I do lock 1 here, I'm indexing into group value 1, sex value 1. Here I'm doing group value 1, sex value 2. And that gives me the sex differences in group number 1. And this will give me the sex differences in group number 2 on all these things. There's some age difference there, but that's interesting, much smaller than this age difference. Yes, hang on. Yes. Yeah, if it was like A and B, I would have, if I had A males, right, that would be like that. Yes, it's a little confusing in this data set because these are numbers, but if they could just as well be like the UIDs before, it could be a string or something.
This is not like index of the column. It's not like column 0 from 0 to something.
Right. This is not the serial order of the columns. This is the value of these index columns, and it could really be any Python value in here. It could be strings. It's actually probably would have been much better if it had been strings in this case. It's very confusing that it's 1 and 2. And for example, I have no idea which is which in this X. Yes.
So you only have 2 groups here, but if you have like 5 groups, is there an easy way to group like 3 of them together and 2 of them together?
Oh, that's a good question. Yeah, so you'd have, I think the question was, let's say that I have, let's say I want on age, right? This is a lot more complicated because there's a lot of unique ages in this. So here you see lots of ages. And instead you want like age groups, right? So maybe you want to group all the really young people and all the older people. And I don't know of a way to do that with group by itself without first creating another column that is age groups that contains those age groupings in it. And I won't really talk about how to do that. There's fast ways of doing that, but I won't want to those here. Yes.
So, I'm very important of it, like this, when you had us with, you were grouping, and then when you were rotating into 1 and 2, that's because the values are 1 and 2, so like if the values for group have been like autism and non-autism, you
Yeah.
use the string.
Yeah, I would do here
Like, that was-
A and male and A and female, right?
Got it.
Right. These numbers are arbitrary in this case. Yeah. This would be, you know, we'd have A, B, and MF here and stuff like that. Yeah, in this case, it's a little weird. Well, let me defer more questions on this topic for a little later, and because we'll have a lot of time to discuss these things. Let me instead just move on to the one next idea here, which I think is really important and cool and useful, because I see we're also kind of this went a little long. The next thing I'd like to sort of throw out there to you is the idea of combining data together, and that becomes really useful and important. That this is Pandas again really shines in doing that kind of operation. Let's say that we had another table with similar data, maybe data from the same subjects. We're looking at these free surfer values, and we also got this other table that is the quality assurance for those 2 unweighted scans that generated those free surfer values. So if we read that table again, this is a CSV table, so we don't need to tell it that the separator is a comma. It does that by default. And now we get, we look, this info method is another way of looking at the properties of this table. It's got site ID, sub ID, it's got SNR, that might be important. So maybe what we want to do is we want to look at the free surfer values of these different groupings, only for people who had a really good SNR in their data. What we notice is that there's what's called a foreign key. A foreign key is one of the columns or keys that is shared among multiple tables and can be used in order to merge those tables together. So that's where we're heading here, is to merging these tables together. I'll first do this data is a little messy, so I'm going to drop all the duplicates of sub ID. I noticed that there's more rows here than in the original table, so I'm going to do some cleaning, very rough cleaning. If I were serious about this data, I'd spend a lot more time on this step, but because I'm dropping data here, I'm dropping every time that the subject ID appears twice, I just drop not the first time that it appears. So I'm just going to look at one scan. I'd like to be a little bit more sure, if I were really analyzing this data, that scan is the one that was in the free surfer table, but I'm not going to do that here. And so now I have a description. I've gone closer. I'm at 1082. I don't know why there are differences in numbers here, but let's leave that aside for now. Instead, what I'm going to say is, let's say that I'm interested in this SNR and CNR tables. I'm wondering what the distribution is. I'm going to quickly just show that Pandas knows how to visualize the data. So it has this is here. I've taken this ANAT QC table. I've selected the columns SNR, CNR. That gives me a new data frame. And on this new data frame, I'm calling .hist, which displays a histogram of every one of the columns, of the values in each one of the columns. So that's good. I'm going to skip over this because we're running out of time here. to just say, if I want to merge the different tables, I can do this operation. The foreign key is called subject in one case in this features table, and it's called sub ID in this other table in ActQC. And if I call merge on those things, I can tell it use left, in the left table, use subject as the foreign key, in the right, use sub ID as the foreign key, and merge those together. And then I will get a merged table that has, in each row, the values pertaining to that subject ID in both tables, which is kind of magical. And there are various ways that that can play out. You can imagine various ways, like what happens if the subject appears in one of the tables but not in the other table. Well, what should I do then? And there are various ways that that gets resolved. Here I'm using sort of the default way to resolve that, called an inner merge, which basically says the value has to exist in both the left side and the right side, and I will only keep, there are only 1,004 rows here. I've basically thrown out all the subjects that are in this QC data, but not in the free surfer data. I've thrown those out here. That's called an inner merge, but there are outer merges and cross merges, and there are other ways that that can play out, which I won't pause on here, except to mention that it's worth reading the documentation. So here's a feature of Jupyter. If you have a function and you hit shift, a tab twice. Ooh, no, it doesn't do that for me. Shift and tab right at the beginning of this parenthesis, it will open the documentation. Sorry, that was shift and tab. I said that various things there. Shift and tab will open the documentation of this function, including, for example, a description of this how keyword argument, left, right, outer, inner, cross, and we'll tell you a little bit about what each one of those does. Okay, and then we can describe this merged thing, and that will give us, the averages of everything, including all these. So you can see here what we got is a table that has all the columns up to the last ROI, and then we start with subject ID, and you can go and you can verify that the subject ID is correct and is equal in every line and should be equal because that is the definition of this merge. And then go and verify all the things that you need to verify. But for now, I'm going to just sort of in one line do sort of a realistic, maybe semi-realistic data analysis that we might do, where we say, take this merge table, look at the SNR column. If it's larger than 10, I looked at this histogram and I said, oh, 10 looks like maybe everyone under 10 is like off the distribution. So let's cut off at 10. Select only those rows, group them by group and sex, and give me the mean. So this gives me a similar table to the one that I had before, but now I've done a selection based on data that came from another table into this analysis. Maybe I've refined the analysis to include quality information in my conclusions, which is worth doing, thinking about Satra's talk yesterday and how hard that is. This can be done here. It is 10, which is when we're supposed to go off for a coffee break. But I will take questions on Slack and in person in just a minute after I break here. But what I want to do, one more thing, is to just mention another theoretical idea here related to pandas, which is this idea of tidy data. Who could object to tidy data? And so it was a good idea when Hadley Wickham wrote a paper called Tidy Data that describes exactly what he means when he says tidy data. This idea, Hadley Wickham is an incredible individual. He's a computational statistician and statistical software pioneer. Who's implemented a lot of software in the R programming language, and he wrote this paper, and people point out quite fairly that this is an old idea from the database literature called this basically what's called in databases third normal form. But tidy data sounds so much more appealing, and he actually describes this much better than anyone in the database literature describes it. So I really recommend reading this paper that is linked from here. Oh, I don't want to do that. Oh, maybe I want to do this. Tidy data that describes exactly what Hadley Wickham means, which is that data should come to us with one observation on each row, one variable on each column, and there are other sort of descriptions in there. It gets a little bit more complicated than just the sentence that I said now, but we can't really work with data in pandas, or it's very hard to work with data in pandas, and you have to do a lot to get to this tidy data before you can do anything of the things that I showed you today. So when you get data, one of your goals should be to get to a tidy data format so that you can do all these things with the data and get to your analysis and visualization in a quick and very fluid manner. It's something to keep in mind when we do the first part of data munging, which pertains to the images from the neuroimaging data and how we process those images. At some point, you really, in many cases, you'll really want to get to this tidy data so that you can do your analysis. And that's a really hard part. Here I've shown sort of the easy part, which is because pandas, you can do all these things a lot in neuroimaging data analysis. A lot of the hard part is getting to the tidy data. But once you have tidy data, you can do a lot of things, and we'll see more things later on in the NeuroHackademy that pertain to the tidy data. So for the sake of everyone's sanity and so that we don't run really late, I'll stop here and we'll take a little break here. I'll come back to Slack in a few minutes after I have a cup of coffee and answer any questions that anyone has about this session. But I think maybe we'll break here, go get coffee, think about all these things, and come to me and ask questions. Ask questions on Slack so that they're there for everyone to discuss and answer. All right, see you in a bit. And then we resume at 10:30 in Alder Auditorium with Angie Laird next, who will Zoom in. So she'll be on Zoom. Right.